Okay, so there's a few things that I want to do. We're not going to go over the quiz. You have the quiz. I don't know, would you agree the quiz was very similar to the assignment that I gave you? Yes. Yeah, it was almost the exact same thing, right? So we went over the assignment. Let me know at lunch or something like that if you have any questions about the quiz. So you have that back. Let's take a look at your equations. Whatever equations that you got done, we can talk about them. Okay, so remember, the Arrhenius or the modified Arrhenius equation, the whole purpose for us writing it down is to explain why is this thing an acid and why is this thing a base. So things like acetic acid, well, we know that it's an acid, but we want to explain what happens when it reacts as an acid. So we know it's an acid. You would have tested that and blue litmus would have turned red. So acetic acid reacts with water, and the water must pick up an extra hydrogen from the acetic acid, so that leaves an acetate ion. Okay? Was that first equation, was that okay? There's difficult. Is that right? Okay. Ammonia, we know ammonia to be a base because it turns red litmus blue. And so the ammonia reacts with water, and usually the first product, but it doesn't matter if it's the first or second, right? But usually the first product we write down is hydroxide. Now if the water turned into hydroxide, it went from H2 to OH. It must have lost the hydrogen. So that means the hydrogen must have been stolen by ammonia, and so the ammonia turned into ammonium, right? All the charges should balance out, right? If you're neutral and you gain a positive, because protons are positive, if you're neutral and you gain a positive, what charge do you turn into? Positive. Yeah, you turn into a positive. Okay. Okay, this one's interesting. Calcium hydroxide, I wrote two equations down because I didn't know which ones you were going to write down. We didn't actually talk about it, and I will never ask you to do the modified Arrhenius equation for what we call a strong base because it just doesn't really make sense. Calcium hydroxide, when we put it into water, doesn't matter if it totally dissolves, does some of it dissolve? Yes, some of it dissolves, and when it dissolves, because it's ionic, it will split up. Right then, straight out of the gate, have we explained how calcium hydroxide makes a basic solution? Have we explained it just using this first equation? Yeah. When this thing dissolves, it makes hydroxide. Boom, we're done. We don't need to react hydroxide with water, because when you react hydroxide with water, what do you get? Water and hydroxide. You know what I mean? The hydroxide steals a proton away from the water, but the water turns into a hydroxide. So you get the same stuff that you started with. You know what I mean? So I will never ask you to write a modified Arrhenius equation for a strong base. I just wanted to kind of touch on that really quickly. Calcium oxide we did earlier, right? Oxide, we're wondering how can this possibly make a basic solution? Well, it steals a proton away from water. The water makes hydroxide. And the oxide turns into hydroxide. All right, no problem. The hydrochloric acid, when you add hydrochloric acid, remember hydrogen chloride is a molecular compound. You cannot ignore the chlorine yet, right? Hydrogen chloride plus water gives you hydronium and chlorine. Okay, I just want to make sure that we've got kind of a little bit of practice doing this because it's on your major assignment, right? I think how many of these types of questions do you have? There's 6 of them, right? So I'm trying to give you as much practice as possible. Okay, sodium carbonate. Ignore the sodium, just carbonate. Carbonate reacts with water to make hydroxide. So the hydrogen must have been passed to the carbonate, so we get hydrogen carbonate. Then we can talk about hydrogen carbonate. Hydrogen carbonate can steal a hydrogen as well from water, turning it into hydroxide, and we get carbonic acid. What's the key in doing these? What's probably the most pivotal thing for you to know about these? What? Yeah, both sides, the charges have to be equal when you're doing these, right? You're not going to be able to start this reaction unless you know if it's basic or acidic, right? So if I said, this solution had a pH of 10, what do you think your first product should be? Hydroxide, because it's basic. pH 10 is basic. Okay, and then the last couple. Hydrogen sulfate is acidic, so it must have given up a hydrogen to the water to make hydronium and sulfate. Sodium nitrate's neutral, so there is no reaction. We just don't have a reaction. Again, I'll never ask you to do it because the question just doesn't make sense, right? And then sodium hydroxide. Sodium hydroxide, when it dissolves in water, does it make hydroxide just by dissolving? Yes, so already we've explained how this thing is basic. You don't need to do the modified Arrhenius because, again, it just doesn't make sense to do that. Okay, we're going to move on. We got two things in general that we want to finish today. We want to talk about strong bases and weak bases, but by association we'll also kind of review. Sorry, John, you're holding your hand up. By association, we will also review strong acids and weak acids. Thank
No, I love this.
I don't know if you can tell, but I don't think I ever would have survived very long if I was a journalist or like an editor or something like that. My proofreading ability is so terrible. You notice it? Yeah, you see it? Oh man, that's horrendous. That isn't a word. That, Watson, come on. Okay, there are some properties that we should already know about acids and bases, and then yes, Akua, actually, probably some punctuation wouldn't hurt, right? Yeah. Let's talk about acids. What are some properties of acids that you know of? Wim, give me one. Okay, theoretically, right? Or I guess, not pH greater than, pH less than 7. What else?
Sour?
What?
Sour?
They taste sour. That is absolutely something that you can test when you're not in the lab. Taste lab. Jesus. Taste sour.
That's how battery acid tastes.
Yeah, battery acid would taste sour, right? I mean, I don't know, so I can't prove it to you. Yes, Stephanie. Yeah, they create hydronium. So theoretically, that's a theoretical property of acids, is that they create hydronium when they're added to water. Anything else? They turn blue litmus red, right? Blue litmus turns red. What was that, Stephanie? It's got a because it has a pH of less than 7, by association, it should have a pH of greater than 7. So its POH needs to be greater than 7 because POHs and pHs are opposite. Now remember, always, if you're trying to figure out if something is acidic or basic, always bring it back to the pH. That's the best way for you to identify, is this thing acidic or is this thing basic, right? We're missing kind of a big one that I don't really care about, and I'm pretty sure I'm never going to test you on it. But acids often are reactive with metals. That's like another diagnostic test, but that's fine. That's okay. When you say acids, often they react with metals to produce hydrogen gas, so that's fine, whatever. Again, you'll talk about that more in Chem 30 because that's a redox reaction. Bases, bases. Let's do the exact opposite of everything on here, right? Basically, Wim? Yeah, they taste bitter. They have a pH of greater than 7. What? I know. Here, let me do everything that you shouldn't do. I'm just going to do this. Perfect. That's way better, right? That fixed it. That didn't make it look terrible. What do they make? They create hydroxide. Or they contain hydroxide, right? When we add them to water. Red litmus turns blue.
Slippery.
They feel slippery. Remember, because bases, they react with kind of the oils on your skin and they make like a soapy substance that becomes slippery. Yeah. They what? They're often just as corrosive as acids. So the further away from 7 you get, the equally more corrosive it becomes. So if you think of a pH of 1, how many pH units is 1 away from 7? So 7 minus 1 is 6. 6 pH units. What's 6 pH units above 7? So 7 plus 6. 13. So a pH of 1 and a pH of 13, they are theoretically equally as corrosive as each other. But it just depends on what substance you're adding them to, right? Like metals, when you put them in a pH of 13, they're probably okay, probably not that bad. But if you put a metal, just your average metal, into a pH of 1, it's not going to last very long because typically metals are reactive. And then finally, they have a pOH of less than 7. But again, bring it back to the pH. Okay, perfect, no problem. So what we want to do is we want to talk about mostly this idea of creating hydronium and creating hydroxide when we're looking at strong and weak acids and strong and weak bases. Strong and weak acids. Have we ever talked about strong and weak acids before? Can somebody give me like a relatively short description of the difference between a strong acid and a weak acid? Could somebody, Idris?
Strong acids are more soluble.
Okay, all acids, as far as you're concerned right now, they're not, but all acids are soluble, okay? So it's not about soluble, but you're on the right track. Stephanie?
One keeps the H and then one gets rid of it in water.
So they both get rid of the H at least a little bit, right?
But one is stronger than the other.
Yeah, one of them we say is stronger than the other. And what we mean by that is if we put the same amount of a strong acid and a weak acid into water, one of them would make more hydronium than the other, right? We define a strong acid to be something that ionizes greater than 50%. That's what we define a strong acid to be. Now, it just so happens that all the common strong acids, they ionize 100%. 100 is just greater than 50. That's totally fine. What's the strong acid you want to talk about? Which strong acid do you want to talk about? Let's not talk about HCl. because we just wrote it down and we dealt with it in the lab yesterday. If that's okay, let's deal with nitric acid. What's the formula for nitric acid? HNO3. So HNO3 on its own, can HNO3 make hydronium? Is it possible for this thing all on its own to make hydronium? No. What do you have to add it to in order to make hydronium? You have to add it to water. Once we add it to water, then this thing will make hydronium and whatever's left over. Do you remember what's left over? The nitrate ion, right? And so we've kind of been doing this without using the slidey finger rule. Do you remember the slidey finger rule? Mm-hmm. Yep. That's where if we added an acid to water, oh man, I'll go all the way to page 8 to 9. Here we go. Boom. So if we add nitric acid, right, the hydrogen gets released and it attaches itself to water, so we make hydronium. But then the whatever's left over, that's what we're going to make, right, the nitrate. Now, we've basically been foregoing the slidey finger rule, and we've been saying, okay, well, let's just figure out what's left over because we have to sometimes. But here, yeah, we're going to make nitrate. This is a 100% reaction. Idris, just to be very clear, all acids will dissolve, but not all acids will 100% react with water to make hydronium, if that's okay. Yeah, Wim?
Like, for example, like once you're with the walls from group 1 and 2, the reaction is that same example.
No, like, are you saying group 1 and 2 metals? Group 1 and 2 metals will never be with an acid. Like a group 1 and 2 metal will never be an Arrhenius acid, if that makes sense. Sorry. Okay, weak acids will ionize less than 50% and often less than 1%. Pick any weak acid in the table. No, we're not going to do acetic acid because we just wrote it down. What? We can do formic acid. The reason why I don't want to do citric acid is because it's a little bit of a nightmare, but that's fine. Whatever. So we're going to do formic acid. HCOOH. Could you spot this from a mile away as being an acid? Yes. Yeah, you could. Yeah, totally. So this is for sure an acid. So it will make water, and it will turn into H3O because it's an acid. What's going to be left over when we do this? Remember, it's the H attached to the COOH that leaves. That's the acidic hydrogen. The other one, the other one isn't. It's not acidic. It takes a lot to be able to remove it. Wim, what was your question? Okay, so this reaction. Depending on the reaction conditions, this reaction is only going to go about 2% of the time. So, which one of these, if I add equal amounts of these acids to water, which one of these will make more hydronium? The top one, right? The top one is going to make 50 times more hydronium than the bottom one, right? So it'll be at least 1 pH unit difference. Hopefully that makes sense. Just for an idea or a visualization of strong acids and weak acids. So we've got 2 solutions, 1 strong acid and 1 weak acid, each at the same concentration. Let's see what happens in the water. We've already done this before, so I'm gonna draw 2 beakers. Let's say we're gonna add 5 moles of each acid. So the first one I'm going to call HS for strong acid. Is that okay? And the second one I'm going to call HW for weak acid. Do you understand why I'm doing that? Yeah. S doesn't mean sulfur. It's not hydrogen sulfide or anything like that. So when I add 5 of these to the water, what am I going to get? When I add the first one of these to the water, what do I get? Does it split up or does it stick together if it's a strong acid? It splits up. They always split up, right? So we're going to get H3O, and we're going to get, S minus. Just whatever the other thing is. Again, it's not sulfur, it's just whatever the other thing is. Then I add another one, and we get H3O and S minus. Then I add another one, and we get H3O and S minus. And I'm starting to run out of room. Hopefully that makes sense. So maybe we'll just add 3 of these. What happens when I add 3 weak acids? With the first weak acid I add, does it split up? No, it doesn't. Probably it doesn't, right? It's just a total probability. So I get HW. With the second one I add, is it going to split up? No, maybe. We're going to say it doesn't. With the third one I add, is it going to split up? Finally, maybe on the third one, it does split up. So we get H3O, and we get W minus. What do you notice about both of these solutions? Or like, what's the big difference between both of these solutions?
One has H3O more.
Yeah, one of them has way more H3O, right? So could you, assuming these were equal concentrations, could you use pH to tell the difference between these? Could you?
Yes.
Is one of these going to have a lower pH? Which one of these is going to be a lower pH? The left side or the right side? The left side is. It's going to have a lower pH because it's got more hydronium. And remember that negative log is like an opposite. So this one is going to have a lower pH. This one is going to have a slightly higher pH. So think of this as being a pH, maybe it's a pH of 3, and maybe this is going to be a pH of 3.9. Do you know what I mean? One of these is for sure more acidic than the other. This is a big stretch. But does anybody know another test that I could do? Does anybody know another diagnostic test that I could use to tell the difference? Wim. I could totally use conductivity. What's the difference? I mean, what makes something conductive? The presence of ions. Do you remember that? If the presence of ions makes something conductive. Do you remember what happened when I added the salt to the water? And the more salt that dissolved, not necessarily the more salt that I added, but the more salt that dissolved, the light bulb got brighter and brighter and brighter. And so is that not the exact same case here? Which light bulb is going to be brighter?
The one to the left.
If I stick a light bulb in here and do a conductivity test, this light bulb is going to be brighter than that light bulb. Would you agree with that? Yes. Okay. So it's going to have a high conductivity. And this one, we're going to say low conductivity, but low doesn't mean none, right? It doesn't mean no conductivity. This just means low conductivity. Hopefully that makes sense. And then there's a picture on the bottom of your page. There's a picture of what's going on when we add these strong acids and weak acids into water. So when I add a strong acid, right, that H and whatever it's partnered with, they totally split up. The H and whatever they're partnered with totally split up 100%. But in here, the H and whatever it's partnered up with, sometimes they split up, or sometimes they don't. So that's the difference between a strong acid and a weak acid. One of these has more ions, one of these doesn't. One of these has more hydroniums, one of these doesn't. Write the modified Arrhenius equation when nitric acid, damn it, makes an acidic solution. We shouldn't have used nitric acid. Let's skip and let's just do ammonium chloride. Let's write the modified Arrhenius equation for ammonium chloride reacting in water to make an acidic solution. So let's take a look. First of all, is ammonium chloride ionic or molecular? It's ionic, right? Yeah. So ammonium and chloride, can we ignore? Because it's ionic, can we ignore one of these things? Can we ignore the chloride?
Yeah.
Because it's an ionic, it's an ion in group 17, we can ignore the chloride. So what's the thing that we care about here? Ammonium. NH4 plus reacting with water. And I don't know, in the question, does it say that it makes a certain product?
Acidic solution. So
It's a- It's an acidic solution, so Cassidy, what are we going to make?
H3O.
We're going to make H3O positive. We're going to make that hydronium. So I'm curious, what's left when we do this? We're going to have NH3 aqueous left. Good. What I want to do is I just want to be very clear, is ammonium a strong acid or a weak acid? Does it appear on the strong or the weak part of the acid table?
Weak.
It's weak, right? So what I would say is I would say that this reaction will happen less than 50% of the time. Because that's what we define weak acids to be. They react less than 50% of the time with water. Now, up top, we're not going to write one, but a strong acid, right? Any sort of strong acid is going to react, we could say, basically 100% of the time. Another way of saying 100% is greater than 99%. And I know that those two are basically the same thing, but they're not really the same thing. 100% and greater than 99% are not really the same thing, but they are pretty much. Okay, here are extra questions if you want. Totally, you could do extra questions. That'd be totally fine, no problem, whatever. Okay, I want to move on to strong and weak bases now. Okay, strong bases and weak bases are the exact same thing as strong acids and weak acids. Except instead of making hydronium, what are we going to make? Hydroxide. So strong bases, what percentage will they turn into hydroxide? 100%. It's strong, it's 100%. That's the idea behind it. So strong bases are ionic hydroxides. Any ionic hydroxide. Doesn't matter, we're just going to define them all as strong bases. For the purposes of Chemistry 20 and kind of Chemistry 30, we will assume that they dissociate 100%. If you look in your data booklet, they don't. If you look in your data booklet and you say calcium hydroxide, solid, this thing has low solubility. But the thing is, we can get this to dissolve more, right? How could we get calcium hydroxide to dissolve?
Heat it up.
We could heat up the solution, right? And so I'm trying to make you understand that it's still, all hydroxides are always strong bases, because you can just heat up the solution, dissolve more of it, and then once it all dissolves, it 100% makes hydroxide. So let's pick anything from group 1 or 2 typically. Any group 1 or 2.
Barium.
Barium, let's do barium, yeah. So let's do barium hydroxide. When I add this thing to water, right, I can force it. I can force it to dissolve if I heat up the solution. So when it splits up, what's it going to make? Barium 2+ ions. And what else is it going to make? It's going to make 2 hydroxide ions. So we don't have to react this thing with water. Water needs to be present to dissolve it, but we don't have to react it with water to explain how this is a strong base. This happens 100%, or at the very least, we can force it to happen 100%. That's what makes it a strong base. Weak bases react with water less than 50% of the time and often less than 1% of the time. I'm going to pick a random base, not necessarily a random base, but I'm going to pick a base out of the base side of the acid-base table. Let's talk about OCl-, hypochlorite. So let's add OCl- to water. This thing is definitely basic. This is what makes bleach so frightening for some people. This OCl- ion, that's what's in bleach. And bleach is definitely a base. So if it's a base, it's going to make hydroxide. And what's left over if we make hydroxide? HOCl aqueous. Because this is a weak base, what can you say about this reaction? What could I put above this arrow? I could maybe put 1%, but we know for sure that this is going to happen less than 50% of the time. Yeah. And I'm just going to use that. I'm going to use this idea of less than 50% or greater than 99%, that kind of thing. So what I want you to do is I want you to write the reactions. Again, strong bases, you don't have to react with water because they just make hydroxide. Weak bases, they will make hydroxide using this process. I want you to try and write down 2. Damn it! We picked barium hydroxide. What other group 1 or 2 ion do you want to use? Instead of barium, what do you want to use? What did you say, Idris? Let's do potassium. Or as Idris likes to call it, potassium. So go ahead and write out these 2 reactions. Remember, when you're writing modified Arrhenius equations, oxide in it already, you don't have to react it with water. But otherwise, you have to react it with water. Ignore group 1, 2, and 17. Strong or weak base. Strong base always has. So strong bases are always something hydroxide. So if the moment you see something hydroxide in the name, that's a strong base. I'm going to interrupt you for a second. What's the very first entity we should write down for this first reaction? So sodium carbonate, right, makes a basic solution, but is this ionic? Yes, so can we ignore one of these 2 things? Yes, the sodium we can totally ignore. So we have to skip all the way to carbonate. Remember, Anything with hydroxide is a strong base. When I say basics, one specific ion should pop it here. Do you want my attention? You want my feelings? Yeah, and so this is a little bit of a stupid question. I'm not gonna lie, because you just write the dissociation of it, and that explains how. Like, keep in mind, I will never ask you to write out this equation because the context just doesn't make sense, right? You already know, Maddie, that we can ignore the potassium, so you just wrote hydroxide, right? We're done, right? You know what I mean? Okay. Ah. Okay. It doesn't have to be your first product, but what should one of the products be here? Hydroxide. Why? Kylan, was it you that said that? Or was it Morgan? It was Morgan. Morgan, why are you saying? Yeah, that's what I thought. I thought it was Kylan. Okay. Kylan, why are you saying hydroxide should be one of the products?
I don't know.
Because I'm telling you this is forming a basic solution, right? Yep. And you've associated bases with hydroxide, and you've associated acids with hydronium, right? Good. And so we got to figure out what's left over. Well, HCO3 aqueous. Am I done? There's a glaring problem with this equation, right? It's that I've got one negative on this side, but I've got two negatives on that side. And when you look, HCO3 definitely is, I don't know where the hell it is. HCO3 is, whatever, yeah, negative, one negative, good. Okay, write the Arrhenius equation for potassium hydroxide reacting to make a basic solution. I'm just saying this, I will never ask you to do this for strong bases, because this question inherently doesn't really make sense, okay? Potassium hydroxide splits up to make potassium ions and hydroxide ions, and we're done, right? This is 100% reaction. What about the top one? What can you say about this percentage? Less than 50%. And again, if the less than and greater than signs are screwing you up, you just write out in the English words less than 50%. That's totally fine. Okay, we're gonna skip some practice. Can I move on? Yeah, we're gonna skip some practice. Is there a test? Is there a test that we could perform in the lab that would distinguish between a strong acid and a strong acid and a weak acid? Lim, give me one test. pH. Yeah, pH paper, I guess. Yeah. A pH test, right? And what's the last one, Cassidy? Conductivity. What I want to know is what variables would need to be controlled in order to accurately compare these two solutions. What was kind of the one thing that we needed to make sure that we keep the same when we're testing
Water.
like the pH. Yeah, the water, sure.
Solution, like we
The
should-
solution?
Yeah, like the well, there's one very specific C word that I'm looking for.
Solvent.
What?
Solvent.
No, the C.
Concentration.
What, Wim?
Concentration.
We need to test these at the same concentration. So if you're saying the weak acid and the strong acid, right? If let's say I'm gonna make up some numbers and they're gonna be totally insane, okay? But let's say you add a weak acid, and let's say your weak acid you were testing at 100 moles per liter. That's an absolutely ludicrous concentration. I don't even know if you can get a concentration that big, but let's say you were doing that. And so let's say your strong acid you tested at a concentration of. Would this be a fair comparison for pH? No. Even though, which one of these normally would make more hydronium, the strong or the weak acid? The strong acid would normally make more hydronium. But if you've got well over 1,000,000 times more weak acid molecules than strong acid molecules, then, I mean, this is still going to be a lower pH, right? The concentration plays a really big factor in the pH of a substance. It's not just which substance you're talking about, okay? So you have to keep concentration. You have to keep concentration controlled. That's the word I'm looking for. That's a controlled variable you would have to keep. Whew. Good? We got 15 minutes to learn about polyprotic substances. And then you can, oh man, look. And then you can finish all of your assignments and all that junk. Okay, some acids only have one hydrogen to give away, okay? We call these substances monoprotic. Does anybody know what the word, like the prefix mono is? One. So one and then protic, what does that mean? Proton. So one proton to give away. For example, let's pick not a very common substance. Yeah, let's pick ethanoic acid. CH3COOH, aqueous. How many acidic protons does this thing have? I see one at the end of the COOH. How many hydrogens are in this molecule altogether, Stephanie? 4. Now, these 3 hydrogens, they're not acidic. They don't act in the same way these hydrogens act, okay? And so there's only one, what we call acidic proton. So it can only give away one thing. Some substances have more than one hydrogen to be able to donate. They have more than one. They can react more than one time. We call these substances polyprotic. Does anybody know what the words poly and protic mean? Okay, so poly means many, and then protic means protons. So it can give away many, or at least more than one, right? I want you to look on that list and try and find a substance that is polyprotic. There's a couple examples that should really stand out in that list.
The hydrogen phosphate.
So when you're looking at it, which one are you looking at? Are you looking at the dihydrogen phosphate? Yeah, is this thing polyprotic? It's got 2 hydrogens at the beginning. Both of these are acidic hydrogens, yeah. So pay close attention to what I'm going to do right now. So please look at the board. the dihydrogen phosphate can give away a proton. What would we be left with? Hydrogen phosphate. Now I can look at hydrogen phosphate. Can the hydrogen phosphate give away a proton? Yeah, that is polyprotic. Absolutely, that's polyprotic. So that's something that could be polyprotic. Let's look at some other polyprotic substances on here. Are there any other substances on here that you see that have either many hydrogens at the beginning or Wim? H2SO3, many hydrogens at the beginning, right? Polyprotic for sure. Yes, I agree with you. H3PO4, many hydrogens at the beginning. Absolutely. What about citric acid?
Yes.
Yeah. How many acidic hydrogens does citric acid have? The C3H5 doesn't count for anything. Those aren't acidic, right? It's hydrogens at the very beginning or attached to a COO. How many COOHs does it have? 3. So citric acid can give up 3 hydrogens in successive reactions. So when you react this with a base, the first time it'll give up 1 hydrogen. So now you have 2 COOHs and a COO minus, right? The second time, now you can take that dihydrogen citrate ion. Now you can take that thing, and if you react it again, you lose another hydrogen. So now you only have 1 COOH and 2 COO minuses. Then you can take that hydrogen citrate ion, and you can react it again a third time and rip off that final hydrogen. Does that kind of make sense?
But you can't do it all at the same time.
You can't do it all at the same time. It's not possible to do it all at the same time. These are separate chemical reactions. You add a little bit of base, then it takes the first one off. Then you add a little bit more base, it takes the second one off. Then you add a little bit more base, and it takes the third one off. But they're 3 very separate chemical reactions. Okay. Okay, an example of one. The one that I like to talk about the most is oxalic acid. Take a look at oxalic acid for me. What does oxalic acid look like? Does this thing have more than 1 acidic proton? Yeah, in the first reaction we can get rid of this one, right? Then in the second reaction we can get rid of that one. With each reaction, the amount of hydronium produced becomes smaller and smaller. So I'm going to write out a reaction, and I want you to pay attention to some of the finer details. So let's say we've got our oxalic acid. I'm going to react this with about as strong of a base as I can possibly think of. What is the essence of base in your mind? Yeah, or just in general, a hydroxide, right? A hydroxide. So the first reaction here, this hydroxide is going to neutralize the very first hydrogen. Do you agree with that? That first acidic hydrogen is going to be gone. So HOOCCOO, and what's the charge on this thing now? If you take away a positive, what are you left with? A negative. And then the hydroxide turns into H2O. This first reaction, okay, anyways, this first reaction is going to be some large percentage. It's going to be really, really, really successful. Okay, so this is going to be greater than 50%. Oh man, I think I screwed that up. Did anybody write in pen? Okay, good. We're going to make some changes to this. I think the intention was for me to react with this with water to begin with. We're going to react it with water. So now, sorry, when we reacted with water, the H is transferred to the water, and we're left with H3O. Sorry. So this reaction, it's a weak acid, so it's still less than 50%. But I'm going to totally make up some numbers. Let's say this goes about 20%. 20% of these actually react with water to make hydrogen oxalate. Now in the next reaction, we're going to take our product, hydrogen oxalate, let's react it with some more water. And when this thing reacts with water again, it's going to donate another hydrogen. So what are we going to be left with? OOCCOO2 minus, an oxalate ion, and another hydronium. Which one of these reactions do you think is going to be more successful? The one with 2 acidic protons or the one with only 1 acidic proton? The one with 2, right? It's got a way higher percentage of actually donating a proton. This is going to be about 1%. With every successive acidic reaction, it becomes less and less and less successful. Hopefully that makes sense. So let's see. I can't remember. Prove that H2SO4 is a polyprotic acid. The way I would prove to you that this is the case, we don't actually have to prove it to you, but the way that I would prove to you, let's look at H2SO4. Where do you find H2SO4 on our table of acids and bases? It's a strong acid, right? So this is 100% reaction. It's going to turn into HSO4 minus. Now this HSO4 minus, can it still give away a hydrogen?
Yes.
Yes, it can. Let's find HSO4 minus on our list of acids.
Hydrogen sulfate.
The hydrogen sulfate. Is this going to react 100% like the first one did?
No.
No, it's going to react less than 50% of the time, right? So, but we did kind of prove that in 2 different reactions, so this is polyprotic. Does that make sense? It's just 2 different reactions. Prove that oxalic acid is polyprotic. We already did that. Okay, no problem. Similarly, bases can react more than one time. And I want to teach you using your data booklet. Is the oxalate ion a polyprotic base? Okay, so it's asking about a base. If it's asking about a base, should we look in the acid column or the base column? The base column. Find oxalate, OOCCOO minus in the base column. It's right around the middle, right? Okay, this time we're going backwards. Can OOCCOO minus, can it act as a base and steal somebody's hydrogen? Yes. Then this thing, the hydrogen oxalate, can that thing act as a base and steal somebody's hydrogen? Yes. Does that make sense? So it is also polyprotic in 2 different chemical reactions. OOCCOO2 minus. You can think of this thing stealing a hydrogen ion, and over here can steal another hydrogen ion. The very last thing I want to ask you, basically the very last thing, is calcium hydroxide a polyprotic base?
Yeah.
And so what I want to bring your attention to is when this thing reacts, when we put this thing into water, how many reactions occur before we make both of our hydroxides? This is a really this is a very tough question for me to be able to explain to you. When this thing splits up, we're going to make calcium 2+ ions, and we're going to make how many hydroxides? 2. Let's think about this. How many reactions did that take in order to make 2 hydroxides? 1. This is not polyprotic. And you need to understand that. It does not react or behave the same way that these other polyprotic bases would
Will
react.
the following students please
When?
come to the office to pick up their life touch photos? Benjamin Wright, Ethan Whitkey, Vincent Ward, Owen Vanderendy, Jacob Taylor, Carson Schultz, Nolan Stang, Chantel Stang, Ethan Stafford, Aiden Sanchez, Marla Reddick, Richard Puzon, Evan Michael, and Mila Machalko. And the following students, will you please come to pick up awards? Zachariah Osman, Gabriel Belzer, Tanner Duderman, Natalie Elgersma.
Okay, you have all the tools in your tool belt to be able to complete that assignment. That assignment will be due on Tuesday when we come back from the long weekend. Wim, what was your question? Wim.
How long is
Lunch is regular time. Your class is going to start until 12:40 again. Yeah, it says all strong bases.
Where are you going?
Very cool.
Good? You get an assignment? Yes, you might know that.
Wala akong bebe. Hotdog.
I swear.